Hello guys, welcome back to Physics with Fazil once again. So we are going to continue our rest of the chapter. All these days we were discussing about dipoles, what dipoles are and how do you quantify dipoles using dipole moment. So that is one of the basic features of a dipole. It should consist of two distinct charge centers separated by a certain length of distance, which is called the dipole length, and one of its to make the situation symmetric, each charge should carry a charge of magnitude q, respective signs assigned to them. So the magnitude of the charge will be q, and we define the dipole moment vector, which is a separation vector between the two charge centers, and it points from the negative charge to the positive charge, and this symbolized as vector d. There are several symbols for dipole moment vector, but meanwhile I am going to use it vector d. So dipole moment of a dipole is equal to the magnitude of charge times the vector dipole length, or the dipole length vector. P equals q times d, and that's a vector equation obviously. Today we are going to study how electric fields are around a given dipole, and also we would learn to derive an expression which we left over in the previous session of electric fields around a given dipole. So before going to the expression itself, let me remind you of what we had done last time. We had a positive charge center carrying a positive charge plus q, and a negative charge center which carries a charge of minus q, and they were separated by a distance, say whose magnitude is d. We wanted to evaluate the electric field around this dipole. For the convenience of marking the location, we did not choose either of the charges, but instead we went to choose the center of the dipole and called it O. Now it was from this O that we started to measure all the positions around the dipole. For example, if I wanted to locate a point here, I drew a vector like this from the center O and marked it or called it some, say, M, a location M in space around the dipole. You could also locate the positions of each charges also. From O, minus q is here, and its position will be vector d by 2. Similarly, the position of plus q, you can call it minus vector d by 2. In fact, it should be plus d by 2 vector on this side and minus on this side, because our d is from minus q to plus q. So anyways, these are just labeling. So meanwhile, to understand the concept, all you need was to just consider them. That's all. And these were the few things you had learned. If you remember this, then we won't require plus and minus q to be written separately. We could just indicate them by the sign. That's enough. And we were not interested in all points around the dipole, because that would generate a very complicated equation which is very hard to derive, as well as it is way out of your comprehension. It is not way out of your comprehension. You could understand it, but it takes time, and for the sake of syllabus to be confined within the limits of an average student, CBSE has introduced or chose only to give you two special cases, and those cases are, one case is on the so-called dipole axis, and the other one was on the so-called equatorial plane. So anywhere on the equatorial plane, the situation is symmetric, because it's always any point on a circle on the equatorial plane is equidistant, right? It forms like a cone from a single charge. So from the other side, it would look like, forgive my bad drawing, but you may understand the situation. It's like the base of the cone, the rim of the cone. Every point on the rim of the standard cone is exactly same distance from the charge. So this is the equatorial plane, and if you remember, every point on the equatorial plane is almost equidistant. Not every point, but the rim, only this rim is equidistant from these two charges. Considering another rim, that's also equidistance, provided that rim is centered at the origin of the given dipole. The origin is the O. Okay, let me not make it any more complicated. So first, we were planning to evaluate field due to the dipole, field due to the dipole where on the dipole axis, on the axis. Okay, so that is where we were planning to evaluate the field of the dipole first. See, you had this dipole over here. Let me make it too close so that you understand what actually these are all point charges. So whatever I am depicting here is actually only an accurate depiction. It's not only an approximate depiction, not an accurate, but an approximate depiction. It's not exactly what it looks like. So let me draw the axis with a blue color line so that you can see it properly. This was our dipole axis. Let me extend it a bit beyond. The origin, let me mark the origin. This was the origin, call it O. This was your plus charge, this was your minus charge. You located a point somewhere here and called it, say, M. So now the position of M will be some position vector from O to M. Okay, so that's your M, that's your point M, and the length of that vector, I'm only going to give you the length of the vector in this case, and it's R. I suppose that was R, right? Yeah, it was R. So distance of the point M from O is R. What was the distance of m from the plus charge, it was some, let me use another color, it was some r plus, and distance of the same point m from the negative charge was r minus. R plus, the plus and minus are on the subscripts, okay. And this distance marked in green from plus to minus charge was d. So half the distance would be d by 2, obviously. D by 2 from plus 2o and d by 2 from minus 2o. So you remember all this. The total electric field at M, E, the total electric field at M, so let me also, so at M will be the sum of electric fields due to plus charge, E subscript plus, it's a vector sum. So sum of the vector electric field due to plus charge and the electric field vector of minus charge, because they are both acting at the same point and should be a superpositioned value. If you remember, E plus, let me show you the point M here. At M, plus charge was somewhere here, this was plus charge, this was minus charge. At M, the electric field E plus should be outwards, right? So because it must be outward because it's due to plus charge. That is what the convention says. So E plus, the vector E plus is in this direction. And what about the electric field at M due to the minus charge? It should be towards the minus charge, and since they are all aligned in a line, in a straight line, which was the dipole axis, the E plus vector and the E minus vector both are collinear. And if you remember, when two vectors are collinear, the total vector's magnitude, which was E, will be equal to the sum of the individual vectors magnitude. So because they are collinear, they act on the same line. Collinear means on the same line, existing on the same line, which you will learn in your max portions. So easy it is, so easy. All you had to do is just add the magnitudes of each electric fields. What was the magnitude of E plus? Let me just give you how E plus magnitude looked. The magnitude of E plus was nothing but 1 by 4 pi epsilon, which I can condense into K. Let me write it with a different color. K, which stands for the 1 by 4 pi epsilon 0. Q, here is plus Q, divided by R plus the distance from the R plus square of the distance plus from the positive charge, from the plus charge. What was E minus? Subscript minus was again here, only the tiny difference is the charge. The polarity of the charge is minus, so minus q k by r minus squared. So these are the two magnitudes. Adding them together putting them into this expression, what will you obtain? You will obtain the total electric field vector is, the magnitude of the total electric field vector is kq by r plus squared minus kq by r minus squared. See, there is a minus here because it was a plus here, but it turned out to be minus because the electric field due to the minus charge carried a negative sign. As you can see the expression, it carries a minus sign. So that is what translates into this equation, the negative value here. As you can see, there are a few common terms involved which you can pick out and rewrite the entire equation like so. 1 by r plus squared minus 1 by r minus squared. But you might remember we had substituted for what r plus and r minus were from the previous class. R plus, let me remind you from this figure again. This much distance is r plus, which I am right now highlighting, the blue one, this distance. So that distance can be rewritten in terms of r and d. How is that done? R is nothing but, r plus is nothing but this much distance being subtracted from this much distance. I hope you can see that, right? If I mark it in black, you can understand. This distance is the total distance minus this small distance, that is d by 2. So r plus was total distance r minus d by 2, and for the sake of r plus, r minus was this total distance, which is nothing but, let me again mark it in some other color. Possibly I can go with yellow because amidst this mess that is much better. This much is r plus, this yellow line represents r minus, and that distance is traveling from here to here, which is r, plus you will have to travel an extra distance d over 2. So r plus d by 2. Again switching back to black, r minus is thing but there is a d by 2 over here. Okay, r plus d by 2. Substituting for those expressions in this equation, see, whenever you stop a equation, just number it. I can since I have not numbered it yet, I can number it, call it 1, equation 1. So that's how numbering the equation works. Whenever we require to stop and digress, we use alphanumeric or Roman numerals to represent the equation where we have paused, and then come back and detail about the equation so that we can refer to the entire equation just by stating its number. So it's kq times what is it? Yeah, 1 over r plus was r minus d by 2 the whole square, and minus 1 over r plus d by 2 the whole square. See, if you go back to your textbooks, instead of d, they may have used a similar alphabet, I mean another alphabet, and that's A. But instead of D, they have used 2A. So if it was D by 2 in the textbook, it would be A. So for the sake of convenience of removing D over 2, they call D as 2A, and then A can become D by 2. So D by 2 would not look a mess in the equation. If you want, you can right now substitute this 2A and A instead of D and D by 2 and carry on, or we can just carry on with the D by 2. See, I'm just reminding you of this. Don't get confused when you read your textbook. This is the symbols. A and 2A are the symbols used for the dipole length. The dipole length is D is equal to 2A. Alright, then coming back to the derivations. Now all we had to do is manipulate everything inside this bracket. It's very easy. It's just you will have to do the LCM cross multiplication stuff. Okay, let us do that. Let me do that for you. If you want, you can pause the video here and do that if you are interested in doing it yourselves, but anyways, I am doing it here. So there was 1 over A minus 1 over B, and the cross multiplication looks somewhat like B minus A the whole divided by, not cross multiplication but LCM, taking the LCM procedure, AB. This is how it looks like. In our case, A was R minus D over 2 the whole square, and B was R plus D over 2 the whole square. Okay, then we had B, which is R plus D over 2 the whole square, minus R minus D over 2 the whole square, bracket closed. Just carefully look at this. It's nothing but just basic multiplication. Whatever was in the denominator was balanced out, and we came up with a single ratio, numerator by denominator form. In the numerator by denominator form, a single fraction. Two fractions we had to add or subtract two fractions, and we made it into a single fraction. Now next procedure is to open these brackets. See, they are raised to the power 2, both of them. So raising anything to the power 2 is just a binomial, is the most easiest binomial expansion. See, in the denominator, let me just simplify the denominator before going to the numerator. See, it is, this thing looks like A minus B the whole squared into A plus B the whole squared. Since both of them have the same power 2, you can commonly write that as A minus B. Let me do it separately here. You can rewrite it as A minus B into A plus B the whole squared. Okay, in this manner, because both of them have had the same power 2. So distributivity of power over products, by the property of the distributivity of powers over products, we can write it as a common power. And inside the square bracket, you can see it is A minus B into A plus B. What is A minus B into A plus B? It is A square minus B square. Now we have the whole square which we took common. So in this terms, the denominator becomes, I don't think this space is enough. Let me just expand it a bit more. but still it should be stay inside the screen. Yeah, I hope you can see that. Let me, so the denominator becomes r squared minus d squared by 4, because it was d by 2 the whole square and d square by 2, and we had the common power 2. In the numerator it is a plus b the whole square and it is a minus b the whole square. So expanding a plus b the whole square gives you r square plus 2 times r d over 2 no, plus d squared by 2 squared, which is 4, and you had this minus here, minus, if you want you can use the bracket before expanding, but yeah, let me just do it in brackets. R squared, it was a minus b form, so r squared minus 2 times r d over 2 plus d square over 4, all inside the bracket. Distributing this negative sign into the bracket, you can see, let me just remove the bracket here itself. Removing the bracket, this minus gets distributed throughout, and that first term was plus r square, it becomes minus r square. Second was minus, it will become plus. Third one is plus and it will become a minus, and this bracket, second bracket, also goes away. We just clear it off, not the bigger bracket, I mean the numerator one, the bracket in the numerator. So what all terms do we have here to cancel out? Let me cancel it using r squared cancels with minus r squared, d square over 4 cancels with minus d square over 4. So as you can see, we are left over with only two terms, and those two terms which we can proceed with are 2rd over 2, 2rd over 2, and both of them are same exact terms. They are repeating like 2 times, so we can call them 2 times 2 times r d over 2 the whole divided by r squared minus d by 2 the whole squared, because oh no, there was no whole square. So here you see there are a lot of 2's here, so we can get rid of one of them. I'm going to get rid of this and this. Anything else? Nothing more. Now as you can see, then the denominator, let me just condense this equation once again. Let me write the final equation in purple. KQ times you had 2 times r rd the whole divided by r square minus d by 2 the whole square. This equation is for every r on the axis, everywhere on the axis this is the equation, but for see, this equation looks a bit complicated too, and it does not involves any dipole moment. Yeah, I can derive a dipole moment from here itself. See, as you can see, let me just mark it in green. There is a q here and there is a d here. What was the magnitude of dipole moment that you have learned? Dipole moment p, vector p's magnitude was nothing but q times d. So instead of this, we can just call it p. Magnitude of vector p is just small letter p. So inserting this into this equation, since they are all in the numerator, you multiply q and d together and you get the above equation becomes, not this one, let me just get rid of this so that you don't get confused with the thing. So you get k times 2 times r times, there was a 2, right? Yeah, there was a 2. 2 times qd. What is qd? Q times d divided by r square minus d by 2 the whole square. Qd is p. So this looks 2 kr p the whole divided by r square minus d by 2 the whole square. This equation is a bit complicated too, because you can see that it is in the denominator you have both r and d separately. So we can do an approximation here. See, this was your O, this was your M on the axis, and this distance was your R, and this is your d by 2. As you can already see, R and d by 2 can be of comparable size, which means the length of R and d by 2 from this figure look almost same. This distance is, though R is bit larger and d by 2 is small. If the point M was inside, then R was smaller. R would be smaller, right? If it was inside the dipole, it would be smaller. But there are cases where the dipole is very small. Let me, yeah, red would be easy. Let this be your dipole. Let this be your dipole, and let this be your dipole axis. Oh, I think I should draw the dipole points after drawing the dipole axis, so that this was your plus, this was your minus. Now as you can see, your dipole axis has been extended way long. Now your dipole is very small. Now imagine you consider a point M over here. Now the R from the center is way larger than, this was R, is way larger than your d by 2 itself. Am I right? See, d by 2 is only this much, whereas R is this much. See, too large. So for a situation where you consider R to be very large compared to d by 2, I mean even larger than this. So let me go back for the approximation. So doing an approximation from this expression, we can go further simplifying by approximating. Let me assume it's somewhere over here on a clear page. Maybe I will go switch on to a next page, not here, there. New page, yeah. Yeah, it's already zoomed in. That's awesome. We start on one corner and we end up on the same corner of the next page. That's some new thing I'm learning about this app. So your approximation is R very large compared to the d by 2 distance, or even you can say d by 2 or d, whichever you prefer, but I would, since d by 2 is been used in the expression, I would prefer using d by 2. I would prefer using d by 2 instead of d. So if R is very larger compared to d by 2, what was the equation? The magnitude of E was k into 2r into p divided by r square minus d square by 4 the whole square. Did I do some mistake in the previous expression? Yeah, see, this is the correct equation. Okay, so if I have done any mistake, like I have put r minus d by 2, then just recorrect it. It's r square minus d square by 4 the whole square. Okay, if r is itself very larger than d by 2, then r square will be extremely larger than d square over 4. This you can verify using simple numbers. For example, you know 4 is larger than, or 4, let me just do some other number. 25 is very larger as compared to 2. Not very larger, it is larger, but still for the sake of convenience. Now square 25, you get 625, whereas if you square just this 2, you will get only 4. As you can see, it is way larger compared to 4. So in a similar manner, yeah, and adding 625 with 4 does not makes any difference. It only makes 629. For a smaller values, 3-digit values, that may seem to be a profound value. Like if somebody comes and asks you, do you want 1,000 rupees? No, do you want 1,000 rupees or 1,010 rupees or 1,008 rupees or 1,013 rupees, 1,000 rupees and 13 with rupees extra? You would easily neglect the 13 rupees or the 10 rupees extra given to you, because on comparison to the 1,000, the 13 extra 13 rupees or the 10 rupees only feels like a bit of a burden to you, so you just easily neglect it. So similarly, I am going to neglect d square over 4, and our under the approximation, the new electric field, uh, let me state it here. The electric field, the value of the electric field for r very larger than d over 2 on the axis is k times 2r times p, the whole divided by what did I do in the denominator? I neglected this whole term, so what I have left over with is r square the whole square. Neglecting means just go away, that's all. We don't need you there. So this is the expression. So r square over r square the whole square is r raised to 4. Oh, there is a 2kp. Let me write the r in the last, because is going to get cancelled out. So r raised to 4 in the denominator, because r square the whole square is r raised to 4. The powers are multiplied, right? That's just basic mathematics. So here in the numerator you have r, in the denominator you have r raised to 4. 1 gets cancelled and you are left over with this. Maybe I can switch the 2 in between. K was 1 by 4 pi epsilon 0 times 2 times p the whole divided by r cube. So this is your electric field. So this is the electric field on the dipole axis for a r very large compared to the dipole length itself. This one inside the box is your examination which you are supposed to be deriving. Either you can write the approximation here, or you can write it over here just like this, r very large compared to d over 2, whichever you prefer. Anyways, you will have to give this approximation. It's only valid for such a case. Now this is just a scalar equation, because you see there is no direction provided here. So what about the direction of this electric field? Where will it be pointed towards? Let us examine the situation again. Plus, minus. See, there are 3 regions. This much is region 1. This is region 2. This is region 3. Let me go with region 1. Here the positive charge is more closer, and the positive charge electric field looks in that direction, points in that direction. Now the negative charge is far away, so say because both are similar, both have the similar magnitudes, the due to the distance, the magnitude of the negative electric field will be smaller. So when you have a larger vector, you subtract it from a smaller vector, you will get another vector which is pointing in the direction of the larger vector. So the E points in this direction in region 1, and that direction is towards in the direction of the dipole moment vector. Okay, coming to the region 2. What is the electric field inside the dipole? Again, you can see in the middle, the positive charges electric field points towards the negative charge, and the negative charges electric field again points towards itself. So both electric fields point towards minus q. So the net electric field will be in the direction of minus q, but which is opposite to the direction of the dipole moment vector, because dipole moment vector should point from minus to plus. So in this case it is parallel to p, vector p. In this case it is anti-parallel to vector p, which is minus p, parallel to minus p, which means it is anti-parallel. And coming to the other side, where is the direction of which is the direction of the electric field? See, as you can see, on this side, any point M is more closer to minus charge. So the electric field which is due to minus q will be pointing in this direction towards minus q, and plus q is far away from M on this side, the region 3. So the electric field must be smaller and should be pointing in the opposite direction. But since they are collinear, and as I have told you before, if you have a larger vector, a smaller vector, and if they are collinear, then their sum results in a vector which points in the direction of the larger vector. So again, on the region 3, it is parallel to P. The electric field on region 3 is parallel to P. So any electric field on the axis would look like this. Here on the plus side, here it will look like this. In between it will look like this, and on the opposite side on the outside of the negative charge, it will look like this. Here it is net E is parallel to the P vector. Here it is E is parallel to minus P, which means anti-parallel to P, and here it is again parallel to vector P. So remember all these points. If you want, you can get a screenshot of this and save it. I mean, there is no need, you can just deduce these ideas anytime you require it. See, right now let me stop this video here. I will be posting another video today evening itself, because already this video is over 40 minutes. So that's all for today's video in this case. So remember all these points, remember the derivation. The derivation will be provided in PDF note, which you can avail through the Google Classroom. Problems related to these portions will also be posted in your Google Classroom. Be attended, and there will be regular points provided which will culminate towards your total internal marks. So thank you guys, thank you for watching my video. Do share your opinions in the comment section, or you can do that with me on private in the WhatsApp. Thank you.